This is an AI-generated fictional video intended for entertainment and education. We live in an era powered by digital brains no larger than a fingernail. Yet creating them requires precision on an absolute atomic level today. Every swipe, every call, and every complex calculation begins here, within the silent, microscopic architecture of the modern silicon computer chip we use. Welcome to the silicon reactor, where ordinary grains of sand are transformed through heat and light into the most powerful tools in human history. Step inside the world's most advanced cleanrooms, where the air is filtered to perfection and the light is tuned to protect delicate microscopic circuits. In this sterile environment, even a single speck of dust is a mountain that could crush a multi-billion-dollar production line instantly and forever. Contrast the slow movements of humans with the lightning-fast precision of robotic arms, working tirelessly to assemble the future of our digital civilization. From the supercomputers that predict our weather to the servers that host our memories, it all originates from this precise and mysterious manufacturing process. The chips born here enable vehicles to see, navigate, and think, making split-second decisions that ensure safety in our increasingly complex and mobile world. Even in the operating room, silicon intelligence guides the hands of surgeons, allowing for procedures once thought impossible to be performed with total ease. This is the journey of the silicon chip, an incredible feat of engineering that turns common sand into the very fabric of our modern existence. Our story begins with quartz sand. While it looks ordinary, this material contains the raw silicon necessary to build the world's most advanced electronics. But this isn't just any sand. It must be refined until it reaches a purity of 9 nines, or 99.99% pure silicon. Inside massive furnaces, the sand is melted at extreme temperatures, breaking down chemical bonds to isolate the silicon atoms into a molten, glowing liquid. Using the Czochralski method, a small seed crystal is dipped into the molten vat and slowly rotated as it pulls a giant crystal upward. This process creates a single, perfect crystal ingot, a heavy cylinder of pure silicon that serves as the foundation for every chip ever made. As the ingot cools, it solidifies into a structure where every single atom is aligned in a perfect, repeating lattice, essential for conducting electricity. Next, the ingot is moved to the cutting station, where diamond saws of extreme precision prepare to slice the crystal into incredibly thin circular wafers. Each slice is less than a millimeter thick. Yet it must be perfectly flat to allow for the microscopic patterns that will soon be etched. The wafers are then polished using a combination of chemicals and friction until their surface is smoother than any mirror found in the natural world. At this stage, the wafer is a blank slate, ready to receive the complex maps of transistors that will give it the power to process data. Each wafer is handled with extreme care, as any microscopic scratch or contamination at this point would render the entire batch completely useless and broken. Thousands of these wafers move through the factory every day, each one destined to become the heart of a computer, phone, or space probe. Now we move from the physical creation of the material to the magical application of light, a process known as photolithography, the core of chip making. Meet the most expensive and complex machine ever built by humans, the extreme ultraviolet lithography system, costing over $200 million per unit. Inside this vacuum, tin droplets are struck by high-power lasers twice to create a plasma that emits the rare extreme ultraviolet light required for printing. This light has a wavelength so short that it can print features just a few nanometers wide, allowing us to shrink circuits to incredible new levels. The wafer is first coated with a light-sensitive chemical called photoresist, which will act as the canvas for the ultraviolet light to draw upon. The light passes through a photomask, which contains the blueprint of the circuit, shrinking the image and projecting it onto the silicon surface with precision. As the light hits the resist, It changes the chemical properties of the coating, effectively developing the image of the circuit into the silicon base. The exposed areas are then washed away with developer chemicals, while leaving behind a physical stencil of the circuit design on the top of the wafer. To give you perspective, these circuit lines are thousands of times thinner than a single strand of human hair, reaching the limits of physical reality. We are now printing billions of transistors onto a space no larger than a stamp, a feat equivalent to writing an entire library on a pinhead. The process repeats hundreds of times for each wafer, building up the complexity of the processor layer by layer through constant exposure and development phases. Engineers monitor every nanometer, ensuring that the alignment between layers is perfect, as a shift of even one atom could cause a total failure. After the pattern is set, the wafer is etched, where plasma or chemicals carve permanent channels into the silicon following the light-printed stencil's path. The remaining photoresist is then stripped away, leaving a clean silicon surface with a perfectly etched circuit architecture ready for the next phase of work. This is where the magic of light meets the reality of matter, creating the intricate pathways that will soon carry the electricity of our digital world. Each transistor acts as a microscopic switch, the fundamental building block of all binary logic that allows computers to process information at lightning speeds. The scale of this operation is breathtaking, involving hundreds of steps and thousands of individual processes to complete just a single wafer's lithography cycle. This shimmering rainbow is the physical evidence of billions of structures working together, a masterpiece of human ingenuity and extreme technological precision and focus. Even at this stage, the wafer is constantly checked, ensuring that the light-based miracle has been captured perfectly without a single flaw in the design. But the silicon is not yet functional. To make it conduct electricity, we must now physically alter its atomic structure through the power of ions. The wafer enters the ion implantation chamber, a high-vacuum environment where atoms are accelerated to incredible speeds and shot directly into the silicon's lattice. These ions act as impurities that change the way the silicon conducts electricity, creating the P and N junctions that make transistors work correctly. By precisely controlling where these ions land, engineers create the switches that turn on and off, allowing the chip to process binary zeros and ones. This process, known as doping, is what transforms a simple piece of crystal into a semiconductor, the very foundation of all modern solid-state electronic devices. Next, the chip needs wiring. The wafer is submerged in a chemical bath where copper is electroplated into the etched trenches to create electrical connections. These copper interconnects are like the highways of a city, allowing electrical signals to travel between transistors at nearly the speed of light for processing. A modern chip isn't flat. It's a three-dimensional metropolis. We stack up to 30 or more layers of metal and insulation to maximize processing power. Tiny vertical tunnels, called vias, connect these layers, ensuring that data can flow vertically through the stack, much like elevators in a giant high-rise building. Looking at a chip's cross-section is like seeing a hyper-dense city from above, with millions of streets and billions of inhabitants working in perfect digital harmony. Every layer added increases the complexity and the capability of the chip, allowing it to handle more tasks simultaneously and store more temporary information efficiently. Signals zip through these pathways billions of times per second, guided by the precise architecture we've built through weeks of careful chemical and physical processing. While insulation is just as important as conduction, we use advanced dielectric materials to prevent signals from leaking between the tightly packed copper wires and circuits. As transistors work, they generate heat. Specialized layers are designed into the chip to help dissipate this energy, preventing the delicate structures from melting down. After weeks of layering and etching, the wafer is finally complete. It is no longer just silicon, but a masterpiece of vertical and horizontal engineering excellence. A final cleaning ensures that every connection is clear. The wafer is now a dense forest of technology, ready to be tested and brought to life. The human brain designed this, but Only the most advanced robots can build it. It is the ultimate collaboration between biological vision and mechanical precision. We now enter the final proving grounds. Not every chip on this wafer will survive the rigorous testing that determines who is fit for the world. A forest of microscopic needles descends, was touching the contact points of each individual chip to send and receive test signals and verify their internal logic. Computers analyze the responses in milliseconds. Green means perfection. Red means a flaw was found, and that specific chip will be discarded or downgraded. Once tested, a high-precision laser or diamond saw cuts the wafer, dicing it into hundreds or even thousands of individual pieces known as dies. A pick-and-place robot carefully lifts the good dies, sorting them by their performance characteristics, a process known as binning, for different final products. The bare chip is fragile and cannot be used alone. It is mounted onto a substrate that will serve as its interface to the outside world. In a process called wire bonding, ultra-thin gold or copper wires are welded between the chip and the package, creating the vital electrical bridges needed. To protect the delicate silicon, a metal or ceramic cap is sealed on top. This also acts as a heat spreader to keep the chip cool. Finally, a laser marks the chip with its name, model number, and brand, the final touch on a journey that began as a pile of sand. This is a finished microprocessor. It is the most complex object ever manufactured at scale, containing more parts than 1,000 modern jumbo jet engines. Billions of these are shipped every year, destined for everything from your smart toaster to the most powerful military defense systems on the planet Earth. The cycle is complete. What was once quartz sand is now ready to think, calculate, and connect us to the vast digital universe we've created. These chips are the silent engine of the 21st century. They power the data centers that store the world's knowledge and facilitate our global communication. Every second, trillions of operations occur across the globe, all made possible by the tiny silicon rectangles we've just seen being manufactured in the cleanroom. Artificial intelligence, the next great frontier of our species, is fueled by this silicon. It processes medical data to find cures for once deadly diseases. Silicon chips allow us to predict the weather with incredible accuracy, saving thousands of lives by giving people time to prepare for the world's most powerful storms. They bridge the gap of inequality, bringing high-quality education and limitless information to children in the most remote and underserved corners of our wide world. In space, these chips are the eyes and ears of our telescopes, capturing light from the dawn of time and revealing the secrets of the universe. But the true value isn't the material. It's the human potential these chips unlock, allowing us to solve problems that were once deemed completely unsolvable. They have turned the world into a global village, shrinking distances and allowing for the instant exchange of ideas, culture, and love across any border. As we reach the physical limits of silicon, a new era is beginning. Researchers are already looking beyond, toward the strange world of quantum computing. Quantum processors use the strange laws of subatomic physics to perform calculations that would take a traditional supercomputer thousands of years to complete today. New materials like graphene and carbon nanotubes may one day replace silicon, offering even faster speeds and lower power consumption for the next generation. Photonic chips, which use light instead of electricity to process data, are another promising frontier that could revolutionize the way we build our computers. The future of computing is not just about power, but about integration. We are moving toward a world where technology and biology begin to seamlessly merge. Brain-machine interfaces, powered by specialized chips, could soon allow the paralyzed to walk and the blind to see through the power of silicon. The micro-revolution that started in the 1950s is only just beginning. What we have seen today is just the foundation for a much greater future. From sand to stars, the silicon journey is a testament to human curiosity and our relentless drive to master the building blocks of the physical world. Thank you for joining us on this journey into the nano world. Thank you for watching our entire video. To make sure you don't miss any in-depth videos, please subscribe, share the video, and turn on notifications.